Welcome to our lectures on the DC microgrid and control system. So, we shall first take out that remaining portion of the previous lecture, that was the energy park and the hybrid charging system. Thereafter, we shall discuss in detail about the stability of the microgrid. Now, the remaining portion of the previous lectures, that is the renewable energy park. The renewable energy park is an evolving concept, and there is an area used for the planning. Generally, it will be now when you go for the city planning, there will be a park inside the city also. Previously, what we used to do, we required to put our power generating unit outside the city, since it is causing a pollution and hazards. And just reverse happens here, it will be a center of the city and it will be a tourism attractions, and you will also generate energy. So, used for the plant for the purpose of the clean energy development like wind and the solar generations. This renewable infrastructure can serve smart and sustainable asset in areas of the surplus industrial property. So, once your places where agricultural land, or you have a sugar, for example, in Uttarakhand I have visited so many sugar factories, they have a plenty of disposable land. So, there they can put the solar panel ultimately and they can use it as a solar park. So, that is also the possibility. The renewable energy park not only provides source of the reliable locally produced energy, but they can also be contributed to the ecotourism, because you require to, since you are generating that place will be clean and all. Serve as an educational source, because you can take them to the excursion to the students so that see that how does the modern concept of the technology works, universities as well as the business group. So, a number of the renewable energy park or renewable energy storage system can be clustered around the common DC bus to form an energy park. So, you will put your all the solar entities and all those things with the power backup maybe into the close vicinity, so that your conduction losses will be reduced. And this kind of the DC systems are sometimes referred to as a collector grid and are used for both photovoltaic and the wind power applications. As appliances with the grid codes often implies reduction of the active power injection to the grid coordination between the multiple generation, which should be achieved its tasks sustainably and the mandatorily. So, that is the one of the constraint that we will put to the energy renewable parks. Now, let us come to the next topic, that is a hybrid energy storage system. So, we require to put in this modern DC microgrid a hybrid energy storage system. The energy storage technologies facilitate high penetrations and integration of the variable renewable energy sources in a microgrid. ESS play an extremely important role in improving the operating capabilities of the microgrids. ESS can be divided into the mechanical, electrochemical, chemical, electrical and the thermal system. So, you can have a different way to, but generally it is electrochemical, mainly it is batteries, but you may have a fuel cell, hydrogen, all those things we have seen in our previous lectures. The most common representative of hybrid ECS is a secondary battery and the combination with the ultra capacitor. Ultra capacitor only take out the energy in seconds, 90 seconds, 100 seconds, something like that, and generally if there is a energy mismatch in hours, that has been taken by the batteries. The capability aspect, the stability aspects of the dynamic properties now. So, the stability aspects of the microgrid refers to the ability to maintain the power supply to load without unwanted dynamics, such as the voltage and the power oscillation. You should not, once load change occurs or something from perturbation occurs into the system, oscillation should not be sustained, because you have a stray inductance in the DC microgrid, and you have within the bus and the ground and within the two bus, depending on the kind of architecture, whether it is a unipolar or bipolar, you have got a capacitance. And thus whenever there is a excitation reactions occurs, and that leads to the oscillations of the voltages, since if it is not damped properly. So, we require to damp those oscillations, and there we can do the passive damping by connecting the resistance between these two buses and all those, but that will be the lossy, and instead of that we can actively damp out. So, by controlling the current flowing to the different point, we can actively damp out these oscillations. Now, that is one of the requirement of the smart microgrid, and thus increase the efficiency. Undesirable dynamic could cause the operation of the protections devices or the breaker fuses, or it may be the transient and it may oscillation is sustained, then it may be detected as a fault by your protection devices, and relay will trip, and ultimately you will throw out the rest of the microgrid in a no power zone, and thus it will turn, which will turn into jeopardize the integrity of the power supply to the list of the sum of the loads. So, that is something, it is not acceptable. If the sustained oscillation is there, those protection devices may activate, and there will be a loss of power maybe in some portion of the microgrid unnecessarily, and thus we require to prevent it. So, dynamic properties, microgrid are the complex systems with diverse response interval and the time delays among this different coordinated control. It may be connected to the high frequency communication channel, thus there is a delay. It may be communicated, some element may be communicated to the low frequency communication channel, and there is a switching delay. There is a response time of different kind of systems, and thus based on that we can categorize that the power generation and the consumption unit will have some delay. So, we have to incorporate it. There is a interconnections between two power generating unit, it requires to have a coordinated control, and internal feedback regulators. So, you have to have a feedback, what it is given, its fidelity required to be checked. So, whether the sensors gives you the right value or not, the fidelity of the sensors required to be checked regularly, and you require to provide some kind of redundancy. The design of generations of the element in the networks and the internal feedback regulators are generally constrained by the dynamics of the prime sources. So, these are something we require to understand that. So, we have the feedback and the regulator will put on restrictions on the prime energy sources, and that will decide what should be the DC bus voltage, something like that. And desirable terminal properties are dictated by the power quality and the generation control. So, power quality is something we have to taken into the account. If you have a solar is more or something, if you have a good amount of if you have a good amount of power is available to you, then you can inject power to the grid. While injecting the power to the grid, you have to maintain the desired power quality, that is the THD has to be less than the something the value which can export power to the grid, as well as you require to have a power factor to be close to the unity 0.95. Those constraint has to be put into the place, then only you can work with the grid. Now, stability. Stability is thus it is an important aspect of our DC microgrid or any system rather. So, it is a part of our dynamic properties. So, stability of the microgrid required to be assessed. One is large signal, another is small signal. So, if it is a huge load change or a sudden phenomena that cause havoc to the microgrid are called the large signal, and the small perturbations are called the small signals. We require to analyze both the stability, then only you can find it out whether it is robustness of the system. Large signal stability refers to the ability of the system to withstand larger perturbation. Now, how you define larger? So, if you are running the load at half of the load, maybe all of a sudden you go to the 100% loading, and you can say that it is a large disturbance or large perturbation. So, that could be caused by the and also by the fault or other rather large step change of the load of the system and settle to the different operating point. Maybe that the once you have 100% loading, you fix the DC bus voltage at 48 volt. Once you have overthrown 50% of the load and you got a generation, maybe you allow maybe 48.5 volt is a new settling point, and that is allowed. So, you stabilize in another settling point depending on your convenient and within a band of the control which you have accepted, and vice versa. In case it can be evaluated by a study of the eigenvalues, so by the normal controller. So, you have to see that we have a what are the values of the eigenvalues you get, roots of the quadratic equations. If you have, you may have any order system, ultimately by the model reduction technique you have to bring down the second order system, then only you can visualize the system better. So, if you have a large order system and go for the eigenvalue and find it out that the eigenvalues positive or negative, based on that you can go for the comment. Or you can apply any standard method like Raoult Harvey's or anything, because if you have a transfer function you can play around. Eigenvalues of the system linearize about the operating point, because it is a nonlinear system. So, you have to linearize it, and analytical tools to study the large signal stability are particularly cumbersome because of the nonlinear nature of genetic microgrid element, because essentially all the elements in the microgrid comes with the power electronics element. Power electronics elements conversion of the power operation of the conversion of power electronics are nonlinear. When you have a on state, there is a one set of state space equation, once it is off state there is another set of state space equation, and thus you come out with the average model. So, for this reason inherently those equations are nonlinear, and thus when you put onto the average modeling, so you accept that some amount of linearization near its operating point. So, that is what it is. For this reason a time series simulation technique would provide a sufficient fidelity for examination of the large signal stability of the system. That is something we may do that. On the other hand, the small signal stability refers to the stability of an operating point under small perturbations. There are sudden disturbances, and that could be caused by the noise or the parameter variations, solar radiation change and all those things. And how system will respond, generally it will settle down to the same operating point. Microgrid can operate into the two main modes which we have discussed several times, that is the grid connected mode and the islanding mode. Each operational mode has characteristics that are directly related within the stability issues. In grid connected mode, the microgrid is connected through a node called the point of the common coupling to a bigger power system, main grid, industrial grid or the national power utility grid or a network microgrid or anything. In this operation mode, the dynamics is imposed by bigger power systems. So, ultimately the frequency will be determined by the external grid, not by you. So, in case of the AC microgrid, since it is a DC microgrid, so ultimately the entry point will be through the active rectifier, and active rectifier will set the voltage of your microgrid through a DC to DC converter. As a result, if it is a AC microgrid, the frequency and the voltage are set and hardly changes with the dynamics of the microgrid. Since your main grid is very rigid, think about the Indian grid, we have only one grid courtesy to the Power Grid Corporation of India. It has got a huge inertia, and so sudden small change in the microgrid, it is not going to affect anything in our main grid. So, since the PCC acts as a voltage reference, it is important to analyze the microgrid voltage profile to guarantee the suitable control strategy that maintains the voltage amplitude within a expected limit. So, once you are exporting power, you have energy surplus, you will be in a one mode, bus voltage may increase, and if you are importing power, then you will be an energy deficit, you will put this bus voltage in a different mode. So, accordingly control will come into the picture. And once you have cut off from the grid, that is quite important aspect. In the islanding mode, the microgrid is disconnected from the main grid due to programmed operation of the it may something that you have you want to you do not you may have if this grid power is so costly that you want to manage by your own generations, or the entry point to the grid has a fault in that case, and this leads to a little complex scenario. The mode of represents a complex scenario in terms of the control and the stability, considering absence of the physical dominance reference. So, who will set the voltage? Now, that is something we have to keep in mind. We have discussed in previous class that there will be a slack node and there will be a selfish node. So, who will be the slack node, and that control has to decide. The microgrid topology, the nature of the distributed energy units and capacity of the storage system play a relevant role in the definition of the control strategies. Now, we are continuing with the stability issues of the microgrid. It is a quite important aspect. The grid forming functions of the distributed generated units, that is the DGUs controller, should adopt by at least one of the converter which imposes an operational frequency and the voltage level for the AC microgrid and for the voltage level for the DC microgrid. The stability issues of the microgrid can be associated with the cause of the different natures, including characteristics and the topologies of the grid, value of the electrical component. So, that is something we have to think of. So, how fast, how, because dynamic response and the stability are generally conflicting in nature. So, we have to choose accordingly its dynamic characteristics and the topological aspects, those issues, power handling capability. If it is isolated DC to DC converter, then how much overloading is possible. So, these are the entities, are the topological aspect that has to be considered. So, if it is operating little bit overloading condition, what will be the losses? So, those all comes into the pictures. The value of the electrical components, the rating has to be comes into the picture, while giving into the some kind of loading, and direction and the magnitude of the flow of the power to the others, whether it is taking power or giving power. So, we have seen a different kind of mechanism in a coordinated control. So, accordingly direction of the power flow also will be decided by the DC to DC converters, and that also play an important role deciding the role. Now, since the energy productions in the microgrid based on the distributed generation usage, the control strategy applied on them are the crucial to overcome the relevant stability challenges. So, that is something we require to understand very thoroughly. For example, control of the voltage deviation. So, how much a tolerance you will allow for the bus voltage to vary, and in case of the AC microgrid or the hybrid microgrid, the frequency recovery and the power flow balance, what we are consuming, what you are generating. Ultimately, results may be transient features may be come from the ultra capacitor or the first response devices, but ultimately you require to balance the power gradually, and the gets worsen in case of the you have many number of the CPLD, that is constant power load. If you have a constant voltage of the loading, then what will happen generally, if you have more loading, little bit voltage will sag down, and thus your consumption will decrease and it will help to stabilize. But in case of the constant power load, once your bus voltage dips, since it continue to consume the same amount of the power, it will track more and more amount of current, and thus things worsen. Based on the interface mode, the DGs can be classified into the power electronics converter interface and directly connected. So, generally we will find that most of these are power electronics converter interface, because the bus voltage and the application voltage does not match. The first category includes the sources as the PV panel, wind turbines, because wind turbine is essentially AC, we require to convert into the DC, and we require to both the cases we require to track the maximum power point, and for this reason we require to have a front end power converter. There are the gas turbine and the battery banks. Battery banks we require to charge in a different mode, because it has to, because you cannot, because ultimately it is a chemical reaction. Chemical reaction charging current should be such that it will simulate the faster chemical reaction. Once you start this process, chemical reaction goes and picks up its peak, after that it will gradually decrease. So, accordingly the charging pattern also required to change, otherwise more heating will be taking place. So, for this reason charging pattern has to be done with the in conjunction with the its property of the material, and accordingly the charging current required to be set. The second category compromises the synchronous and the induction generators, such as used in a diesel generator or the small hydro units. So, these can be directly connected to the DC bus voltage, where field can be controlled by the field excitation. Now, let us talk about little bit small signal stability, and that is quite important, and we require to, and if it is not stable, then it will have a sustained oscillation, and sustained oscillation may trip some relays and all other entities. Stability uses this stability, small signal stability uses a relatively small perturbation. Those are called the small and the transitory load changes, system damping, the distributed generated units power capability limitations, and the feedback controller mismatch. So, there might be issues with the fidelity of the sensors, all may be put into this actually small signal stability problem. It may be working very fine, but your sensors may be capturing little wrong data. It may be so that you find that irradiation is such, and unfortunately irradiation is been measured by the sensors that tilted angle is not properly placed to track the sunset radiation, and thus there is a mismatch. So, you predict that something will come and ultimately you find an error. So, the MPPT tracking will be erroneous. All the interactions of the control systems in the DGs can cause local oscillations. It is necessary to analyze in detail effect of this perturbation on the system stability. These are few aspects of the small signal analysis. Now, in case of the, because we require to, since we have a set of the differential equations and thus we write a state space model, and state space model we use all those power electronics devices. So, you have on state and off state, and thus we require to have average modeling. An average model is essentially a linearized modeling. In this case, a linearized models of the microgrids are useful, especially considering the unique characteristics of the renewable energy, renewable distributed sources as intermittency in the energy generation. So, it may change all of a sudden. So, solar irradiation may change, wind may change, state of SOC of this battery may change, and thus to account this intermittency comes into the pictures, and that can be well captured by the linear model. To overcome the stability issues related to the small signal perturbation, some common control strategy, very simple PI controller or any or PID, that will work fine. Are additional control loops and coordinated control of distributed generations are being preferred, which may help to give us the robustness of the system in presence of the disturbance. So, closed loop control will ensure that this disturbance has been mitigated, damping can be possible, sustained oscillation may be damped. So, another aspect is the transient stability, that is quite important aspect of it. So, we have a sudden load change, we have a sudden state transitions from on grid to off grid, all those leads to the transients, and thus we require to analyze the transient stability in detail. The transient stability analysis of the microgrid can ensure the system operability after the large disturbances. Generally, this is caused by the large change in the system. With micro sources of the current limit, a little spinning, since you have put that current limiter in every places, very little spinning reserve and limited reactive support, because voltage cannot be boosted by the reactive support in case of the AC microgrid. It is essential to carry out the detailed transient analysis with possible contingencies, with the possible limitations. If the grid is used as a backup system when generated and the storage power of the microgrid are not enough to supply the required load, that may be your point of action, the control system should correctly design to allow smooth transitions without the causing the stability problem from off grid to on grid and vice versa. On the other hand, nonlinear system model can be used to assess the transient stability. So, we require to understand that this system, since it is a large load change, your operating point will change and the system is totally nonlinear, the average model will not work. And thus transient stability technique as a construction of the, we require to put it as a energy functions, that is a Lyapunov stability functions, and we have to analyze that how energy goes down, so that the system will be more stable. This allows the identification of the control parameter ranges where the stability is guaranteed, that it is a Lyapunov stability at large. That is something we are trying to conclude. Sometime we simulate it, but we require to do a proper simulations tool for it. The simulation of the critical scenarios is key, that is called the Monte Carlo programming. is key to design the stage to reduce the risk of the instability caused by the transient. So, that is something we require to be designed for the contingencies. So, that transient can be taken care of nicely by your control system. Thank you for your attention. We shall continue with the more applications of the DC microgrid in our next classes.